My name's Tim Gorringe. A few faces I know here, most faces I don't know here, but hopefully I get to meet you over the semester. Um, Welcome to Physics 508. I'm going to start by just saying a few words about the course structure and the course content of 508. And we're actually due together the very first assignment in 508. And then I'll move on to the first introduction. There's going to be two classes of introduction to Python coding. So this will be the first one. Thursday will be the second one. That's going to kind of lay some foundation for the physics problem solving that we're going to get on with over the rest of the semester. Just so you know how to contact me, my office is in the chemistry physics building. It's on the third floor. It's basically nearly above the bagel shop. It's room 309. If you want to email me, this is the best way to email me at timgorange@uky.edu. I posted my office hours here. They're Mondays and Wednesdays in the afternoon. But if those times don't work, you can just email me and set up an appointment, or you can drop by them there most of the time. So those are probably the best ways to contact me. Okay, so I said I would start with just a little bit of course organization and just a little bit of course content. And actually the very first assignment, which is the Hello World assignment. You might have seen it. So this overhead just lists the things that you're going to need for this class. You're going to need access to Canvas, the Canvas course. That's where, for example, I post the assignments for the course and where you submit the assignments for the course and where you'll see your grades for the course. So you need access for those reasons. It's also where I put things like the lecture notes, and if there are any lecture videos, and other related materials. So that's all in Canvas. So you definitely need that. You need, I mean, this is computational physics. You need a laptop. It could be a Windows laptop or a MacBook, or it could be a Linux laptop. All those are perfectly fine, because we're going to work with Python as a coding language, and we're going to work with Google Collaboratory as our coding environment. And so basically your laptop is your kind of window to Google Collaboratory, which is your window to Python and the notebooks that are the assignments in the course. There's no textbook for the course. There are actually a number of free textbooks that you can find online. I put links in the Canvas course. There's a lot of other free resources that are online, like lectures and videos. I put links to those in Canvas. So there's a lot of material out there, but I'm not specifically using a particular textbook or following a particular textbook. Just the course structure. So by virtue that you're here, you know that it meets Tuesdays and Thursdays at 10:30 to 1:45. So that's our meeting times. Most classes, maybe not this one's classes, but most classes will involve kind of what I was calling a mini lecture, where I talk about a physics problem or a physics topic, and I talk about numerical methods, numerical techniques for solving that physics problem, that physics topic. So we'll do that. It turns out that it's not always mini. Sometimes it was more than mini, but it is, I'm calling it a mini lecture. And then we'll move to the assignment for the class. I'll do a related assignment for the class. So I'll do some live coding of a related assignment, and hopefully that will set you up and help you with the actual assignment that you'll submit for the class material. So that's kind of the organization. Um, as I say, the basic idea of the class is that we're going to be exploring physics problems. That's the focus. We're going to be exploring physics problems through computational numerical techniques. That's really the focus. And it's not a class that is about coding and programming. Although this week I will be introducing some coding and programming. But the class is really not about coding and programming. Each class will have a assignment associated with it, and you'll submit that assignment by submitting a link to your notebook that contains the assignment into Canvas. So you submit assignments by just submitting links to your Google Collaboratory notebooks. And the way it works is like this week we'll have today's class Tuesday, Thursday's class. There's some assignments from today's class and Thursday's class, and you'll submit those, and those are due by next Tuesday, by 2 p.m. next Tuesday. And then the same cycle goes on and on and on, right? So next week there'll be Tuesday class and Thursday's class. There'll be assignments for Tuesday's class and Thursday's class, and you'll submit those the following Tuesday by 2 p.m. And we just keep doing that on and on. And so that's how it's going to work. And those assignments will form your final grade. This is just a word on course grading. So every assignment is worth the same number of points. It's just worth 10 points. We'll see an assignment, the Hello World assignment today, that is a trivial 10 points, but other 10 points are more costly 10 points. But every assignment is 10 points. I'll total up at the end of the semester and midterm your number of points. 90% guarantees an A grade in the class, 80% B grade in the class, and so on. So that's how the points are allocated and how the grading is done. There's no midterm exam or no final exam. It's all just Google Collaboratory assignments, solving physics problems. And so that's how we're going to grade the class. Any questions on all that? I mean, that means I'm either really clear or really unclear. Something. Yes.
When will we get our ratings on homework back?
When so you're submitting a link, and the grader will review your solution, and then the grade will be posted in Canvas and should be posted within a week. Try and keep, it's easiest to keep up with it, right? And so hopefully you, by the time your next assignment is due, you have the grade from the prior assignment. So that's the goal. Any other questions? Okay, so let me say a few words about course content then. What are we going to do? One way to think about computational physics is to think of it as one of kind of three branches of physics, right? There's theoretical physics, there's experimental physics, we know that, and then you could think about computational physics. So that's one way you could think about computational physics. Maybe another way of thinking about computational physics is that, well, there's experimental physics and there's theoretical physics, and computational physics is a tool that's used in experimental physics and theoretical physics. So it's really a wrapper around experimental and theoretical physics. That might be another one. Computational physics, one thing that it does is it really expands and broadens and deepens the sort of physics problems, the physics questions that we can tackle, that we can answer. So it kind of extends our range beyond pen and paper to tackle more complex, more sophisticated problems. So that's one thing about computational physics. And I remember, I mean, 100 years ago or whatever, um, going at high school physics, and I had this feeling that every physics problem was solved by pen and paper. That's how you solve physics problems. But it turns out that most physics problems, probably almost all physics problems, are not solved by pen and paper. And it's very easy to turn a pen and paper physics problem into a more complicated, more sophisticated problem that you need computational methods and numerical methods to solve. So you can turn if you take the problem, pen and paper problem of a simple pendulum, swing to and fro. If you just swing the pendulum with a larger amplitude, you turn that pen and paper physics problem into a computational numerical problem of solving it. And that's true of many everyday types of problems. Drop a object to the ground. If you drop it from a large height, you've turned it from a pen and paper problem into a computational physics problem, a numerical problem. So most problems, straightforward, simple pen and paper problems, will quickly turn into more complicated, interesting, sophisticated computational problems. Over the course of the semester, this is just the list I made here. We're going to talk about use computational methods to solve linear equations, we'll solve differential equations, we'll look at random processes, we'll look at many body processes. So that's kind of a big span of physics problems. And we'll take them from all sorts of areas, from classical mechanics, from thermodynamics, from electrodynamics, and much more. We're also another application of computational methods is where you kind of investigate physical data. You investigate natural data and you pick out the patterns. You recognize the patterns by computational methods. So an example of that might be, when Galileo realized that all bodies fall with constant acceleration, it was based on measured data of the position of falling bodies versus time. And he saw in that data the underlying signature of constant acceleration. When Kepler determined that Mars follows an elliptical orbit, he determined that from measured data on the celestial position of Mars in the night sky. So he was able to interpret it, see the signature of the elliptical orbits in the coordinates, the celestial coordinates of Mars. And computational physics opens up a lot of tools from Fourier analysis and statistical analysis and regression analysis to look at data, look at measured data, physical data, and see and explore the underlying physics beneath that data. And so we'll be doing that. So we'll be doing Fourier analysis, regression analysis, statistical analysis too. Okay. As I mentioned, we're going to be using Python and we're going to be using Google Collaboratory. Why? A reason to use Python is that it's very quick and easy to learn. I was able to learn it, so it's very quick and easy to learn. And if you know Python now, by the end of the week, you'll know a lot of the Python we need for the class. So it is quick and easy to learn. There's some things about it that make it quick and easy. And I won't go into the details right now, but you'll see those later. One one thing about it that's very useful in physics, one thing that's powerful in physics is that, in physics we have physical quantities, which in computer programming you're going to represent as some sort of variables. And Python has natural to Python or native to Python is a lot of physics-like variables. So it has, obviously has integers and floating point numbers, but it also has vectors and matrices. It also has complex numbers. And so it has all the tools, all the types of variables we need for physics problems. So that's one reason to use it. Another reason is that Python comes with a vast number of packages and libraries that have been written for use in Python. And these provide really sophisticated tools for things like visualizing data, things like plotting data, things like visualizing, plotting results from calculations. And so that's another reason that we'll use Python. The reason we're going to use Python in Google Collaboratory is that's an easy way that we can all use the same environment is one thing. So no matter whether you've got a MacBook or you've got a Windows machine or you've got a Linux machine or you're going to try to do the course on your Kindle or whatever, we're all going to be working on Google Collaboratory in the same environment. And so any examples I show you of me working through assignments, I'm working through them in exactly the same way as you're working through assignments. So that's a positive thing about that. The other thing is that it's a practical thing. With Google Collaboratory and Canvas, it's very easy for you. It'd be very easy for you to submit your Google Collaboratory notebook into the Canvas assignments. So the sort of handling of submission and grading, etc., is going to be very straightforward, hopefully. So where are we going? The very first assignment, and this was listed as the very first module in Canvas, is a Hello World assignment that's just going to introduce us to Google Collaboratory, to notebooks in Google Collaboratory, and how we submit assignments. And so I'm going to, in a few minutes, I'll just do that assignment in front of you. Some of you have already done it, so you're going to be bored. But others can just follow along and submit it. So we'll do that. That'll just take a few minutes. This week and next week are dedicated to getting us ready for sophisticated, complicated physics problems that are going to be the rest of the semester. So this week is kind of dedicated to learning the Python coding that we need for physics problem solving. And I can do that in just we can do that. We can do that in just 2 classes. We'll work through the essential Python coding that we need. So if you don't know any Python right now, by the end of the week, you'll know all the Python you're going to need for the rest of the semester. Next week, we're going to do the same sort of thing, but for what I would call visualization, plotting, and modeling of data. We're going to introduce a bunch of libraries. Maybe these words mean nothing to you right now, but matplotlib you'll know by the end of the semester. Pandas you will probably know by the end of the semester. A bunch of Python packages, libraries that allow you, open up the opportunity to plot data, visualize data, model data in very sophisticated ways. So I'm going to introduce this sort of world of data modeling, data science, data simulation in the second week, next week. And then we get on to physics sort of the physics problem solving, sophisticated physics problem solving. Okay, any questions on all that? Okay. The first assignment in the course. So this is an assignment. Assignment number one that's due next Tuesday. That assignment is to write your first. Yeah, I mean, if you've not met Python, to write your first Python code, and it's this code that says "Hello World." So let's just go ahead and I'm gonna introduce. So the idea of this assignment is to write the Hello World Python code in Google Collaboratory and submit it to Canvas. You have to be able to do a number of things. You have to be able to go to Google Collaboratory, to open a notebook, to write a line of code in your notebook, and then to be able to submit it as a Canvas assignment. So this is really an assignment about the mechanics of how we do our assignments and submit our assignments. Okay, so this is my Google Drive, and you'll want to go to your Google Drive for your assignments. I think just to keep myself organized, I'm going to make I turned over a new leaf of organization for my life, and I'm going to go and make myself a new directory in Google Drive for this class. So I go over here, I'll make a new folder. What shall I call it? Physics 508, why not? Okay, so I made myself a little directory, and you probably want to make yourself a Physics 508 directory, and I'll go in here. And of course, it's empty because I've done nothing yet in Physics 508. But I'm going to do my first assignment. My first assignment is to write this code that prints "Hello World." So I'm going to now make a notebook, Python notebook, in as a file in this directory. So again, I go over here. I got to go to more. And here we are, look, Google Collaboratory. I could have made a Google Doc or a Google Sheet or a Google slide, but no, for this class, I'm going to make a collaboratory note. Okay, let's thought it wasn't going to open for a minute and that I would not be able to do my own first assignment of writing Hello World, but it did. So here's what the notebooks look like. You may be very familiar with the notebooks. You may not know what they are. Upstairs here, just to mention a few things. This is the file name for the notebook. And to avoid having lots of untitled notebooks, I'll call this Hello World. So that'd be the name of this Python notebook. And then down here, this is a cell. There's actually two types of cells. There's cells in which you can just write text, so you could describe what you're doing in text, and then there's cells that you can input your Python code. And this is that's a code cell. And so you can pick code cells, add text cells. This is a code cell. And I'm just going to put print, which is a Python function. We'll see later, it's what I would call a native Python function. It takes a input. We'll talk about input later on. The input is what it's going to print out, hello world. And this is my first Python assignment, my first Python notebook with my first Python code. Let's imagine that. Let's imagine this was the first time I've done it. We can run this code with this little button over here on the left-hand side that runs the cell. So there's one way you can run it. Just thinking about it. And it ran it. And look, it printed out hello world. I didn't even have a bug in my first code. I could have run it from this menu bar upstairs here. There's run all. If you have many cells, you can click, for example, run all, and it'll run all the cells. But I've only got one cell, so just run that one cell. Anyway, so now I've completed my first assignment, but of course I better to get credit for it. I've got to submit my first assignment. And so the way you're going to submit your assignments is you're going to share with me and the grader a link to your assignment. So upstairs here in the top right-hand side, you see this share button. So I can go here and I am able to, by copying the link in the bottom left here, I'm able to share the link to my notebook. Now, to share your notebook with me so that, for example, I can run your notebook to check your code runs, for example, we want to allow anybody with the link and to have editor privileges and be able to therefore run the notebook. So the link you're going to share with me is one that anyone with that link can not only view your code, but also run your code. So let's copy that. And then let's go to assignments. Now in the Canvas page. Here's assignment number 1. And let's pretend I'm a student. View as student. Oh, well, I already did it. I don't know if I can do it. I can't do it again. But in here, this is the assignment, and you would submit a link. You see, I've already submitted my link to this assignment. And then you're done. It's off to the grader, and the grader, as we just discussed, within a week, we promise, is going to grade your assignment. I guess I can give a new attempt, yeah. Okay, so I've submitted my assignment. Any questions on all of that? Okay, that was all the introductory type material I want to cover. I wanted to just tell you about how the class was organized, what the class is going to contain, and I just wanted to show you that I can even do the first assignment in the class and submit. So, as I say, this class and the next class, we're going to be introducing some Python coding. And when we introduce Python coding or we introduce numerical techniques, we're going to be also introducing some physics problems that we'll be solving. And I'll do that in this class too. So let me imagine now we're really beginning the class. Got through all the administrative stuff, all the organizational stuff, how to do this or that. Now I'm going to begin the class. Okay, so this is Python Coding Introduction Part 1. Thursday's Python Coding Introduction Part 2. In Python Coding Introduction Part 1, I want to cover variables, what they are in Python. I want to cover assignment statements, what they are in Python. I want to cover functions. We're going to talk about functions a lot, what they are in Python. And I want to cover what I've written here as packages and libraries, which are going to be very important for us in Python. So I want to introduce all those things. As a physics, I always want to have some sort of physics or scientific application. As a physics application, I'm going to use gravity as a simple application and Galileo's free fall law and Kepler's third law between the period and the radius of planetary orbits. I picked those two because those are good examples for introducing variables, assignments, operations, functions. I also picked them to, well, what are the very first things that you meet in a general physics class? Well, the first things you would meet in gravity is literally the free fall law and Kepler's law. So these are some of the very earliest things we've ever met. We're just going to now solve problems involving free fall and Kepler's laws computationally. I also, though, want to advertise that this is a case where, free fall law, applying that is a pen and paper problem. Kepler's third law, relationship between the period and the radius of orbit, that's a pen and paper problem. But this problem involving gravity, interacting bodies and gravity and motion is very easy to turn into something that is not a pen and paper problem, but rather is a computational physics problem. So I want to show you that too, because I want to showcase or I want to advertise what's coming up in the class. So that's the topic here. So I'm going to advertise that beneath the free fall law, beneath the Kepler's third law, kind of at the roots of those two laws, is really a world of differential equations, many body problems that we will only be able to solve computationally numerically and cannot solve with pen and paper. Okay, so when we come to the coding, the two laws I'm going to, here's the free fall law. It's just the relationship between the distance fallen and the time taken for a falling body like an apple. That's Galileo's free fall law. Here's Kepler's third law. It's an equation describing perfectly circular orbits and the relationship between the period of the orbit and the radius of the orbit here. In a way, think of these two laws as two equations that describe the trajectories of objects under gravity. So the free fall law is describing the straight line trajectory of a falling body under gravity. And the Kepler's third law is describing the circular trajectory of a planet or the moon in circular motion under gravity. So there are equations that describe trajectories associated with motion under gravity. At their heart, at their core, is the both of them, right? Is the universal gravitational interaction that acts between all massive bodies, and the laws of motion that relate force acting on a body to the acceleration of that body. So that's the heart, that's the core of the free fall law and Kepler's laws. But free fall law and Kepler's law are very special cases, very, very special cases of motion under gravity, according to universal gravity and laws of motion. So for the free fall case, that law, y equals 1/2 gt squared, where did that come from? Well, formally, in terms of it coming from universal gravity and the laws of motion, formally it comes as a solution of a second order differential equation that it arises when you have an object under falling in uniform gravity near the surface of the Earth. So that leads to a second order differential equation. And the free fall law is a solution of that, a special case solution of that equation. Similarly, the equation for the Kepler's third law for the circular orbit, that also what underlies that is universal gravity and the laws of motion, but they lead to a differential equation in which the centripetal acceleration causing the circular motion is given by the universal gravitational force between, say, the Earth and the Moon, or the Sun and the planet. So again, Kepler's third law is kind of a solution, special case solution to a second order differential equation based on the laws of gravity and equations of motion. So both free fall and circular orbit are results of trajectories arising from solutions to differential equations based on universal gravity and laws of motion. But they are very special cases, right? In general, you have gravitational interaction between bodies, then the motion in general, if you've got two bodies, the motion is not straight line motion or perfect circular motion, but parabolic motion or hyperbolic trajectories or elliptical trajectories. So these two simple equations are just two very special cases, but there's a whole world. There's an infinite world of different hyperbolic, parabolic, elliptical orbits that are solutions to the gravitational interaction between two bodies. The world of the elliptical orbits, the hyperbolic, parabolic trajectories, involves solving a more complex solution to differential equations. And we're going to see that this is a case where we can easily solve that more complex problem numerically in our Python codes. And we can do it with the coding that we develop in this class and next class. So in this class and next class, we'll be able to do the coding to be able to solve the elliptical, parabolic, hyperbolic trajectories of the general two-body problem. In fact, this is basically an outline of how we would do it. When we solve the problem numerically rather than analytically, what we do is we turn the differential equation into a difference equation or difference equations. The difference equations tell you that how the position of a body changes, how the velocity of the body changes in some small little time interval. So you imagine these difference equations allow you to calculate the change in position of a body. Maybe it's the apple, maybe it's the moon, or maybe it's the Earth in some little time interval. They allow you to calculate the change in velocity of the object. Maybe it's the moon, maybe it's the apple, maybe it's the Earth in some little time interval due to gravitational interactions. And if you can calculate the change in position of the body in some little time interval, let's call delta t over here. If you can calculate the change in velocity in some little time interval based on the gravitational interaction, then on a computer, all you have to do is keep repeating that process over and over and over again, many times, hundreds of times, thousands of times, to solve the trajectory. So numerically, computationally, the solution to these difficult analytical differential equations. It's very straightforward. It's sort of a algebraic arithmetic problem, basically, of calculating for each little time step, each tiny time step, how the position of a body has changed, how the velocity of the body has changed, and just asking the computer to do that time and time again. Repeat that, repeat that, repeat that over and over again. So it's with some very simple computer arithmetic, we can solve the general case of these differential equations. And so that's what I'm outlining here. And as I say, all that you need from Python coding to solve the general differential equations for the gravitational two-body interaction is the coding that you get in today's class and in Thursday's class. And then you can code up these sophisticated problems. Actually, even more impressive, this is the three-body problem. So Apple falling to Earth is an example of a two-body problem. Moon orbiting the Earth, example of a two-body problem. The interaction of the Earth, Moon, and Sun, that's a three-body gravitational problem. That is a problem that Isaac Newton famously failed to solve. He wanted to solve the problem of as an application of his universal gravity and laws of motion. He wanted to solve the problem of the three-body interaction between the moon, the Earth, and the Sun. And he famously failed to solve the three-body problem. So that step from two bodies to three problems became a problem that two-body case is analytically solvable. The three-body case in general is not analytically solvable. Later on, after Newton failed to solve the three-body problem, special case solutions were found. So for these famous mathematicians, French mathematicians, Lagrange, Euler, they found, Euler wasn't French, I don't think. I don't know. I don't know who these. I don't know how to pronounce their names, and I don't know where they came from. But anyway, these famous mathematicians did actually come up with some special case three-body orbits that you could describe analytically. So they're kind of like the equivalent of the free fall law, straight line motion, or the circular motion, perfect circular motion, as being two special case solutions of the two-body problem. Euler's and Lagrange's solution to the three-body problem, I'll show you them, are special case solutions of the three-body problem. But it turns out actually that in general, there's no analytical solutions to the three-body problem. This is a case where we've just gone from two bodies to three bodies. The only way possible to solve it is numerically. And so you have to come in this class to be able to solve a gravitational three-body problem. In all the other classes where they're solving things analytically, they can't solve the three-body problem, which is a very basic step from the two-body problem. So one of the features that was pointed out by another French mathematician, Poincaré, was that maybe he's not even French, but I somehow associate France with all these names, is that the three-body solutions have a feature in which the motion is extremely sensitive to the initial conditions that you release the three bodies with. And that feature is described as a chaotic behavior. So the motion of three bodies under gravity is a deterministic system. There's nothing indeterministic about it, but it's kind of an unpredictable system. It's a non-predictable system because it's very sensitive to the initial conditions, the initial positions, locations of the three objects, the initial velocities, speeds of the three objects. A familiar example of this is weather forecasting, right? Weather forecasting is also very sensitive to initial conditions. You can predict the weather a few days in advance. So maybe you can predict it like in 10 days in advance, but you can't predict the weather a year in advance or 10 years in advance. It's too sensitive to the initial conditions. So the gravitational free body problem is a classic example of the weather forecasting problem that is so sensitive to the initial conditions that you can't predict far into the future for the three bodies. Okay, so we'll also see that this three body problem is something that we can solve with a little bit of programming we're going to learn this week, which is basically a little bit of Python arithmetic, a little bit of Python control statements that we'll do in the next class, and we'll be able to solve the three-body gravitational problem. But even you'll be able to solve it in a couple of hours. And Newton spent half his life trying to solve it. So that's the power of numerical methods and computational methods. Okay. I just think I want to, just to prove it, I actually wrote a little code based on arithmetic from today's class and based on the next class, control statements in the next class, and solve the three body problem for myself. And I made a little video of three examples. So this is Euler's example of where there is an analytical solution. I've got three bodies interacting under gravity, and they're arranged in a straight line here, and they're obviously attracting one another, and we're just going to watch them evolve with time. And if you start the ones on the left and right symmetrically, then this is an analytical solution to the three body problem. You see the one in the middle stayed where it was originally positioned, and the others just circled around it on opposite sides of the body in the middle. I didn't want to go to that. I want to go up here. This is this is Lagrange's analytical solution. Again, I got three equal mass bodies in blue, red, and green. Again, I've arranged them this time in a triangle, but another sort of symmetrical arrangement. And I'm going to fling them out symmetrically. And again, I'm solving this. I made a video of it, but I did solve this in Python, this three body problem. And this is the other analytical solution for the three body problem. You see that they were heading outwards symmetrically, but of course they're attracting one another. So they're going to fall back inwards kind of symmetrically. And this is Lagrange's solution. So these two solutions are like the straight line motion and perfect circular motion for the three body case, where there are simple analytical solutions. And I'll show you one more case. I mean, once you've got the code, you can launch any sort of three body problem that you like. I think this was another one I did. Yeah, this is where I didn't launch them entirely symmetrically. And what you see is I started with those three bodies, but they've kind of formed this binary pair here. And this is one of the interesting features that happens in three body interactions, that often, you can try this out, I've tried this out many times, that they form binary pairs. And it's very hard even to look at it and predict which pair is going to form the binary. And then sometimes the binaries will split up and you get another binary pair. Anyway. So in 1 week, you can be doing that. Let me stop this. Okay, all that, well, the videos were motivation. This is meant to be a motivation for why I want to sit through the remainder of the class, which is talking about arithmetic in Python. The reason for doing that is that with that arithmetic, we can solve interesting problems like this. Okay. I think I'm going back over here. I thought I titled that. Yeah. This is back to that directory I created where I did my very first assignment, right? And I'm going to start a new assignment. So assignment I set myself is to take the free fall law, Galileo's free fall law, describing, say, the apple falling to Earth. And I'm going to calculate, based on the length of time that the apple's fallen, how far the apple has traveled. So I'm going to use the free fall law to calculate that distance fallen in a certain amount of time as a way of illustrating variables, assignments, arithmetic, input, output in Python. So let's start a new notebook. I'll give this I'll call this free fall. And I'm going to calculate distance. So I'll put that in here too. Now, the distance fallen in a certain amount of time, I'm going to calculate from that formula y equals 1/2 gt squared. I'm going to have to input a time taken. So this program is going to involve input. And I'm going to have to output the distance fallen. So it's going to involve output. So I'm going to have input and output. This equation is going to involve variables. So distance and time are variables, but acceleration, yeah.
Or the seem like producing some noise. Yeah, maybe you didn't stop it.
Yeah, I think you're on the YouTube.
This is head.
Oh, yeah. Thank you. You mean here?
Yeah.
Yeah.
There.
Thank you. What am I doing now? I've got to find my way back. Here we are. Yeah, that was a good catch. Thank you. So I've got to define some variables for position and distance and also acceleration of gravity. And then I've got to do some arithmetic to calculate the time distance fallen in a certain time. And I've got to do this input and output. You know, a Python code is a series of instructions that the computer executes one by one. And so this is going to be done by a series of instructions that get executed one by one. Physical quantities like the distance and the time and the acceleration of gravity are going to be represented by variables in Python. And Python variables, you can think of a Python variable as kind of like a little container or a box, like a shoebox, in the computer's memory, where in that container box in the computer memory, you're going to store a number that's associated with that variable. So associated with acceleration of gravity, I'm going to associate 9.8 meters per second squared as the number. And so we're going to introduce variables. G equals 9.8. G is the name of the variable. 9.8 is the value I'm assigning it to. And G equals 9.8 is an assignment statement for that variable. It assigns the variable G to the value 9.8. So there's a shoebox inside the computer's memory, and we've just stuck 9.8 inside that, that shoebox. There's various types of variables. So there are integer variables, 1, 2, 3 integers, well, you know what they are. there are floating point variables. This is a floating point variable with a decimal point. There are other variables. There's variables called strings, which are text variables that can be made up of alphanumeric characters and other characters. Those are string variables. So there's lots of different types of variables. And as I said, other types of variables are complex numbers, are matrices, are vectors, and so forth. So there's a function called type that's Python native. It's native to Python. You'll see what that means later, where you can use that function with an argument, G here being the argument, to tell you the type of the variable, because Python automatically assigns a type based on the variable value that you've inputted. And so if I run this again, or if I run it, it tells me that I set G equal to 9.8, so obviously a floating point number. Python interpreted it as a floating point number. So it's a type called float. If I had made G 10, then Python associates that type of variable, because it sees the 10 without the decimal point, associates it as an integer. If I had input 10 as text, then it associates it as a string, right? A string is just alphanumeric other symbol text. So Python is automatically interpreting what type of variable, integer, floating, or string your variable is. Inside the computer, different numbers of bytes are used to, and different formats of bytes are used to store integers and floats and strings. Anyway, we're on 9.8. We want to input into our code the time that the object falls for, and we're going to output from our code the distance the object fell. So we want to input something and we want to output something. Let me show you how to input something. Input a variable, input a quantity. I'm going to put this in a new cell, but we'll talk about more about the structuring of cells and the arrangement of the cells later on. But for now, I'm going to put each line in a new cell. But that would be a kind of later on, you think that's a kind of a bizarre or strange thing to do. Okay, so I want to input a variable, which is going to be the type. And you do that with another function, a native function. It's called the input function. And the argument of that function is some text that you want to print out. Enter time fallen. And that function will return the quantity that is input and assign this variable t to that quantity. Let me show you. Let me run this. Oh, so when I run this, it runs that input function. That's going to ask the user to input a value. And physically, it's the time fallen. I'll put in 2 seconds. And it sets t to be equal to that 2. But let me just show you that the type that it assigns t to be. So we talked about the type function. Let's look at the type of t. when you input a quantity with the input statement, whatever the quantity, whether you input a integer or you input a floating point number or you input a string, input always interprets what you've inputted as a string. So although I inputted a floating point number, I inputted 2.0, it interpreted that as a string. If you want, now we want this to be a floating point number, the time taken for the object to fall. What we have to do is convert that string to a floating point number. And you can do that with another native function in Python that is just called float. And it will convert, in this case, this string into a float. Oh. So I'll enter the 2.0. And now the type T for our variable is a floating point number. Okay, so now we've defined a constant, the acceleration of gravity. We did that in the first cell. We've defined this input variable, the time that the object is falling for. We've done that in the second cell. Now we want to, and again, I'll make it in a separate cell here. We want to calculate the distance fallen. So this is a basic bit of arithmetic. And what was the formula? Can I remember it? It's 1/2 times g, the acceleration of gravity, times the square of the time. So this is also a assignment statement. So is this big enough actually to see? It is fine. I mean, I could make it. Let's make it a bit bigger. This is also an assignment statement, but it's assigning y, this variable y, and its values to a arithmetic product involving these two other variables, the acceleration of gravity and the time taken to fall. When you have an arithmetic statement like this, right? The native functions that you can use are, well, you can add a plus sign, you could subtract with a minus sign, you can multiply and divide. There are a few other native functions that you can use in Python, and I'll talk about those later on, but we're just using these native functions here. Notice to square the time, to multiply is 1 asterisk, to square the time is the pair of asterisks here. So that's going to calculate the distance fallen for us, so we can run that. Of course, you might be interested in what type of variable that is. So we could ask the question, what type that is. That's a floating point variable. The rule is that if we were just doing an integer calculation here, the result would be an integer. If we have floating point quantities over here on the right, then it's going to be a floating point variable here for y. If we had complex quantities over here on the right-hand side, then y would be a complex variable. The variable on the left is its type is the most general form of the variable on the variables on the right-hand side. So if you have integers and floats, the variable on the left-hand side, the y will be a float. If you had floats and complex numbers on the right-hand side, the variable on the left-hand side will be a complex quantity. So it's the most general form. Finally, we want to print out the results. I'll put this in another cell. And we talked about input, a native function in Python to input quantities. Now we want to use print,
which is a native function in Python to output quantities. So I'm going to print what y is. We've already used it in the hello world, but we didn't explain it. I want to print the value of y. And we find that in that 2 seconds, you've fallen 20 meters. So you're kind of, if you fall out of a window and you think, I've fallen for 2 seconds, that doesn't seem too long. You've fallen a long way and you're going quite fast. So you've fallen 20 meters in that time. You can print in more sophisticated fashion the results. So for example, I can print a string followed by the value of y to sort of annotate the results. So I can add a string, separating it from the variable with the comma here. I could, I should always put in the units. So I could add another string that says the units are meters for this quantity. And so on and so forth. So in this one little example, free-for law, we've introduced variables, different types of variables. We've introduced input, output. We use the native function input to input from a user a number into our code. We use the native function print to output quantities from our code to the user. And we've looked at arithmetic statements. We've talked about how integers, floats, and other quantities are stored in the computer, whether integers, floats, complex quantities are assigned to a variable, and so on and so forth. Any questions on all that? I want to introduce one more thing, I think. I'll do it with a new code. And that's Python packages and Python libraries. That's I think the other thing I wanted to do today. And I think I'll do that I'll use the free-for law as an example again. But we'd turn the problem on its head. This time I'm going to calculate, in these last 5 minutes, I'm going to calculate the time taken to fall a certain distance. So I'm going to take y equals 1/2 gt squared, and I'm going to rearrange it for t and solve for t given the time that the object falls for. So it'll be the square root of 2 times the distance fallen divided by the acceleration of gravity. Okay. Remember, this was me getting organized. This is my Physics 508 directory. I'm going to start a new code and now remembering where notebooks are. This is also free-for law. But this time I'm going to calculate the time. Okay, so let me go ahead and write this. I'm going to enter some of it quickly because we know how to do a lot of things. We know about variables, assignments, and arithmetic in Python now. So I want g equals 9.8. I want to this time calculate the time fallen. It's time taken to fall a certain distance. So I rearranged the free-for law for the time. We said it was the square root of 2. I go again. What I do? I've got to get in the value of y. We put that in first. It's input. Distance fallen. Remember, input gives us a string. I've got to convert the string into a float to make the variable y a float. So I'm going to encase the input statement, which is a native function in this other native function float. So that'll give us the value y. Let's say it fell 20 meters. And now I want to calculate the time that it took to fall that distance. So now is when I want to calculate t based on t being the square root of 2 times y, that's the distance that we've entered, divided by the acceleration of gravity. And that's just the rearranging of the free fall law. And so this is our code, and then we can print it out. So let's run that. So that didn't run. That didn't run because if you look down here, Python's telling us it doesn't understand what square root is. So Python understands native arithmetic operations like addition and subtraction and multiplication and division and some more. But native Python doesn't understand what square root is. It also doesn't understand what a log or an exponential is, or a cosine or a sine is. We have to what we call import this function, square root function here. But if we were to use sine or cosine or log or exponential, we'd have to import it from a Python package. And so that's the extra ingredient that we got to use in using the free fall law to calculate time from distance that we didn't need when we're calculating the using the free fall law to calculate distance from the time taken. In one case, we were good with all the native functions in Python. In this case, we need to import some non-native functions. So I want to show you how to do that. So let's go up here. I'm going to add right at the beginning an import statement. Let me show you one way that we could do it. From numpy import square root. So what is this saying? What this is saying is there is a package out there, a Python package out there called numpy. It contains a lot of functions in it, a lot of mathematical functions. We're going to be using it time and time again. One of the functions it contains in it is square root, that enables you to take the square root of a number. So we're going to import from this package or library numpy, we're going to import a single function, the square root function. And then we're going to use that function to calculate the time downstairs here. And then we should be able to print out the result for the time taken to fall. So now let's run the whole code again from the beginning. Oh, but I'm going to have a problem down here. We said 20 meters. And we get that it now was able to execute the square root, and we printed out the fact that it took 2 seconds, just over 2 seconds for this distance here. And so this is using this imported function. So this is one way to import an individual function. So that would be a nuisance. Supposing you were using square root and log and exponential and sine and cosine, that would be a nuisance to import all these functions individually. So an alternative is to import the entire library. And the way you would do that is to import numpy and you as and then you give it a name, and everybody uses MP. So this imports the library numpy and gives it a code word or an alias, NP, something that's short and easy to remember. And then when you call the square root down here, you have to tell it it's in this library that you've aliased to MP by not just writing square root, you would write MP period square root. So it's telling us, look for this function square root in this library whose name you alias to NP. So now if we run this whole code, 20 meters we were going to fall. We find, again, 2 seconds. So it's able to pick out the square root out of the entire library and use that. And so this is just a brief introduction to importing packages or libraries, using packages and libraries in your code. And we'll look at this some more in the next class. Anyway, I want to end there. Any questions on today's material? Yeah.